Hello, everybody. Today, I'm going to talk about the MoChA pipeline and how you can use it to perform phasing and imputation of DNA microarray data in the cloud. So as an introduction, um, what is phasing and imputation? Well, for every genome-wide association study where we work with DNA microarray data, we always have to go process the data through three main steps. The first step is to call genotypes from microarray intensity data. Then we have to retrieve the haplotype structure of the samples by phasing. And then we have to impute the missing variants that were not present in the microarray by imputing, by comparing the haplotypes that we phased with haplotypes of another reference panel of samples for which we have more information. And phasing and imputations in particular are two steps that require a fair amount of computations and parallelization of computations due to the high computational requirements. And there have been many pipelines out there to perform these two steps. But today I'm going to talk about the MoChA pipeline, which consists of two different scripts. One is the MoChA WDL and one is the impute WDL. The first one performs calling genotypes and phasing, and the second one performs imputation. These scripts are written in WDL, which is a language for workflows, and allows you to define very complex sequence of tasks. A WDL in particular corresponds to a set of tasks and a description of the order in which the tasks have to be performed. And in the writing of the task, we have to define which input file we need, which commands we're going to run on those files, and which output files we expect. And the nice thing about writing pipelines in the WDL language is that they can be run on any computational environment. In particular, you can do this thanks to the Cromwell workflow engine, which is an engine developed at the Broad Institute. And the idea is that you can input your WDL pipeline into the Cromwell server, and the Cromwell server will take care of dispatching all the required jobs to different nodes in a highly parallelized fashion. And these could be nodes on an HPC cluster, like an SG, LSF, Stormcast cluster that are common in academic environments, or maybe in cloud computing cluster like Google Cloud, Amazon Web Services, or Microsoft Azure. And this is all transparent to the user that doesn't have to worry about the technicalities of the cluster implementation when writing a WDL pipeline. So what features does the MoChA pipeline for phasing and imputation have that might be not available in other similar pipelines? Well, the first feature is that it follows a minimalistic approach. So the user only has to provide the minimal amount of necessary inputs to run the pipeline. It can take very different input files, but in particular, it can process raw Illumina input files, also known as IDAT files, without requiring to be processed in alternative ways. It uses very state-of-the-art software for phasing and imputation shipped for Impute 5. It allows you to use the reference genome of your choice, so you can just request the GRCH38 as the reference that you want to use. And once you have set up a Cromwell server, or you can actually even run the pipeline in Terra if you want, it's very easy to use. And it scales very nicely and seamlessly to a course of a biobank size. And so in particular, you can run it on the UK Biobank, and the phasing part will run for less than $100, and phasing imputation overall will run in less than 40 hours if you run it in Google Cloud. And the reason I actually developed this phasing imputation pipeline was to support analysis related to mosaic chromosomal alterations. So in particular, when you run this pipeline, you're also going to get as an output a list of constitutional mosaic chromosomal alterations in the samples you process. So how complicated is it to run the MoChA pipeline? Hopefully I can convince you that it's not that complicated. The running a pipeline mostly means that you need to define a set of input files. Let's say that we're going to run a pipeline in IDAT mode, and we're going to provide a set of IDAT files, um, which are again Illumina intensity files. We're going to have to provide that, and we're also going to have to provide a table with a list of samples and a table with a list of batches. And then in particular, we're going to have to provide a configuration file in JSON format indicating in which way the pipeline needs to be run. And once we input that into the Chrome wall server together with the MoChA WIDL script, the output we expect is going to be a set of VCF phase files and an output table with the list of these files. So this is an example of what the input for a run is going to look like. Here we have a sample table. Each row is a sample. Here we have a batch table on the bottom left where each row is a batch. And for each sample, we have to define which batch it belongs to and which green and red IDAT file it corresponds to. And for each batch, we have to define the 3 different manifest files from Illumina, which are the BPM, CSV, and EGT, which inform the software about which variants have been tested and about what the clusters for each genotype look like. And the configuration file, which is in JSON format, is going to define just a minimum set of parameters, like the name of the cohort, the mode, which in this case is the IDAT mode, because we're inputting IDAT files. In this case, because the manifest files are in GRCH37 coordinates, we will ask the pipeline to realign the manifest files. This comes very handy when Illumina does not provide manifest files for GRCH38. And then we can provide information about how much parallelization we want to achieve in phasing. So we can define the window size, the maximum window size for phasing, which in this case would be 50 centimorgan, but we can decrease that if we want to parallelize the computation even more. And then after that, we need to provide file URL addresses for where to find all the files for the human genome reference, for the Illumina manifest files, for the IDATs, and also for the 2 tables. And that's it. Once we have these 3 files, we can just submit the MoChA WIDL together with the configuration file into the Chrome wall server with a command like that. And then if everything goes well, we would obtain as an output a table with a list of VCF files, and the VCF files that will be generated will be divided across batches. And so for each batch, we're going to get a VCF file with the phase, genotypes, and probe intensity, and then also a VCF file just with phase genotypes useful for imputation. Then we'll also get some summary plots that will visualize the call rate across samples and maybe some statistics that will indicate possible contaminations. And then also other summary plots indicating probe intensities for the sex chromosome and other that I'm not showing now. The cost that I've observed, if you run it in Google Cloud, is of about $1 per 5,000 samples for GSA-like arrays. Similarly, running the imputation pipeline is not that different, especially after you've run the MoChA WIDL pipeline. We're going to have to input a set of phase VCF files, 1 per batch. We have to gonna input a table listing the batches, and then again a configuration file listing some important options. And again, this will be input into the Chrome wall server together with the impute WIDL script, and we're going to expect a bunch of imputed VCF files out if everything runs correctly. This is an example of what an input would look like. And again, a batch table file in tabulated format where each row contains information for 1 batch. And then a configuration file here on the right where again we can define parameters like the name of the cohort, which chromosome we want to impute. If we don't want to impute all chromosomes, if you omit these, all 23 chromosomes will be imputed. And then information about, for example, which kind of information do we want in the output imputed VCF files. Do we want the dosages, and then we can ask for dosages, or do we want genotype probabilities, or maybe we don't want either and we just want the genotypes. By default, the imputation pipeline will use the fuzzy genome coverage reference panel, but you can also input a reference panel of your choice if you want. The only requirement is that you have access to the reference panel, and that it's structured in VCF format split across the 23 different chromosomes. And again, a simple command like this will submit the job to a running chroma server, where we indicate that we're going to run the impute WIDL script together with a JSON file with the configuration up here. If everything goes well, we're going to get as an output again a table with a list of VCF, and we're going to obtain one VCF for each batch and for each chromosome that we have asked to impute. The pipeline, as I said, it uses impute5 to run. Optionally, use BigO5 if you need to run it in a commercial settings and you don't have a commercial license for impute5. But impute5 is free for academic research. And the cost, if you use the Fuzzy Genome Project reference panel, is about $1 per 1,000 samples when you run it in Google Cloud. Now I'm going to show you very quickly some applications of the MoChA pipeline. And so first of all, this is a list of biobanks across the world where we were able to run the scripts thanks to collaborators that have access to the data on some of these biobanks. I personally already have access to the UK Biobank and the Massachusetts General Brigham Biobank data. Something you might notice is that because of different restrictions with different biobanks, we actually had to run the pipeline on very different array of computational environment, from LSF and Slurm clusters to Google Cloud European clusters. But this is a testament to the fact that the pipeline that we structure actually can run on almost any biobank. Moving on, there will be more pipelines in development. There is actually a polygenic score pipeline that can be run right on the output of the imputation pipeline if you're interested in computing polygenic scores. And there is, as a work in progress, a association pipeline that will run regioning in a very distributed fashion and will take again as an input the output of the MoChA imputation pipeline. Part of the reason why I've been developing this set of pipelines is that about 5 years ago, I started to work with Prolo on a project to detect the mosaic chromosomal alteration in the UK Biobank. And to our surprise, we found that there was a lot of interesting biology to be discovered by doing so. And for Nature paper after that, I started to realize that there was actually quite some interest in running this kind of analysis with mosaic chromosomal alterations on biobanks. But the technical skills to actually do that was really prohibitive for many users. And so I decided to try to package the analysis that Peru had done into an easy to reproduce framework. And that led to the development of the MoChA pipeline. However, although it is designed to scale to biobank size dataset, it can be applied also to a smaller cohort. And this is an example of work from Maxwell Sherman that applied the framework on autism probands, and he was able to show that mosaic chromosomal alterations are more common in autism probands compared to their unaffected siblings, even if this explains only a very small fraction of autism probands. And to conclude, the MoChA WIDL pipeline supports virtually all computational environments. It follows a minimalistic design, and it can input IDAT files. It can be used on GRCH38 without further hurdles, and they can scale to biobanks of any size. And if you're interested in CMV analysis, it actually will provide germline and somatic outputs for further study. And with that, I would like just to acknowledge the many people that have helped in the development of this framework. To start, I want to thank my supervisor, Stephen McCarroll, that has supported me for many years. Prolo, that has run many of the initial analysis on the UK Biobank, showing that this framework actually is important. And then the many collaborators and users of the pipeline that provided the incredibly important feedback. With that, I'll conclude. And I understand there will going to be a Q&A session after this, so I'll be available for questions if you have any. Thank you for listening, and I hope this pipeline might be useful to you.